So I think we can start. Let me press the recording button. Just a few things about the test. So most people pointed out that they were unable to get the exact eigenstates of that operator that I had given you. So what I've decided to do is that let me just write what you were supposed to get. So the energies E, L, and M. This will be given by, the first part is easy to get, L plus 1 h bar squared. Then you had to add, this was the tricky part, B squared plus C squared M h bar. But because most people were unable to get to that point, what I will do is that I will only give maybe 6 of the marks I will give only if you had tried to compute the correction. So the first order correction was 0, and the second one you found to be, at least I found it to be C B squared B M h bar. So if you could show me that you understood the work and you were able to get to that, I don't see why I should be penalizing people for not being able to do the first part of the problem. And then the other problem was with uh, the problem with the Gaussian. I have a feeling that you might end up having to solve maybe a quadratic equation. I'm still writing the memo, but if that is the case, I think if you could set up the problem and show me that you can compute things like t plus v, and that you understand that you had to try and minimize um, that image as a function, I think maybe it might be a function of alpha. I think for 5 months I will give you those marks, even though most people will not be able to complete the entire question. And then I think for the rest, I've browsed through your script. I think most people get the work. So even the last question on time independent motivation field, I see that people are able to do those types of problems. So today, what we will be doing is that so far we have, for example, at one point we were talking about the interaction picture, and we were computing things like the Dyson series, and all those things are largely theoretical. Today, what we will be doing will be seeing how what we have been doing actually relates to experiment. So the thing that experimentalists are interested in is this thing called the differential cross section. So let me just try and explain what that would be. So the way that if you remember your modern physics course, the classic scattering experiment, I think it was one of the first one, was the one done by Rutherford. So what you do is that you have a bunch of incident particles, and then you send them through to some target. Right. Now these particles, so there might be a potential that has a certain range. So once it's outside of that range, then it's 0. Some of these particles are not really going to scatter, so they will pass through the target without any deflection. But there are certain particles that will be scattered, and what you will be interested in, if you look at a certain area element, you're interested in the number of particles. So that are measured at a certain direction, which I'm denoting by theta and phi. Now, what will happen is that this number is not really a sort of a good quantity to be dealing with, because it's proportional to your incident flux. So then the one that you will end up working with will be what is called the differential cross section, the sigma over the omega, and this will be then the number per incident flux per unit time. the number of particles that are passing through that direction, theta and phi. But in a sense, you've normalized it by dividing by that J incident. And another thing before we continue is that the calculations to compute these things are easily done in the center of mass frame, whereas the measurements are actually done in a lab. So you have to move between the omega, the sigma over the omega. You first have to find a connection between the center of mass, which is the one that's very easy to calculate, and the one for the lab. And that's what I first have to do. And just one final thing. So the relation between d sigma and sigma is obvious. It's just you just integrate out the differential cross section over d omega, and d omega, I should say, this is just the usual theta d phi. So once you integrate that, so you'll end up with just integrate over the usual angles. But as I was saying, the calculations are easy in the center of mass frame, or in other words, the frame of reference where the center of mass is not moving, but calculations, but everything is being done in terms of everything is being measured in the lab frame. So in the lab frame, you have a particle, which is M1, and you have another, and the target is usually stationary. So this will mean that V2L is 0. And after they've collided, so the target and also the other particle M2 might be moving. Say you will call that the speed VL1 prime, similarly for the other one V2 prime. And then in the center of mass frame, the center of mass will be at rest. So the standard thing that you do for classical mechanics, so you define RL1 as R1. So these are the coordinates of the first particle, but they will be this R vector, which is just the position of the center of mass. Then you differentiate that equation. So this will give you the relation between the speeds. So this will just give you V1 L given by V1C plus R plus V, the velocity of the center of mass. So, and similarly, once you have had your collision, you have the same relation, but now with primes there. So if then you look at in terms of components of the angular momenta, so let me just erase. So you basically are looking at that picture, which is I'm labeling A. So that will give you a relationship between just like V1 cos theta 1. So give you V1 prime C cos theta plus V center of mass. And similarly, if you look at the y component, VLY prime sine theta given by V1C sine theta. So these are just standard first year type of equations that you will get by just looking at the momenta. Once you have these two equations, then let's just call this equation 1, that equation 2. So if you divided equation 1 by 2, you will end up with V1 L prime sine theta 1 divided by V1 L prime cos theta 1. This just gives you a tan theta. Tan theta 1 will give you sine theta over cos theta plus V center of mass divided by V1C. This is the equation. And then what I want to check is that I want to express these ratios in terms of the masses, maybe M21 or M1. So this the center of mass is just M1 x1 plus M2 x2 over M1 plus M2. Then once you differentiate, then you will get that equation. Then you plug it into this equation, right? So this will give you something like V1L given by V1C plus M over M1 plus M2 V1L. Then you can solve for this V1C. And you repeat the same thing, but in the center of mass frame, the center of mass is not moving, so everything will be 0, 0, 0. Then this gives you a relationship between V1C and VL, and then you just divide this equation by the one that I called 1. So if you look at that equation, it's expressing V center of mass, and remember that you're looking for the ratio VCM over V1L. So if you just divide those two things, you end up with this, and then you just plug it into the equation that you started with for tan theta. Then if you recall, cos theta is given by 1 over sec theta, and which is just the square root of 1 plus tan squared, and you already have that. So this will be a 1 there. Then once you plug everything into the equation, you end up with an equation for cos theta. And the reason why we wanted to do this is that the relation d sigma over d omega, this should be the same either once you measure it in the center of mass, because it's basically measuring the number of particles that are being scattered into that differential area element. So once you get this, you get d sigma over d omega in the lab, d omega in the lab. Right? So in order for you to solve them, you have to find what is d omega in the center of mass divided by d omega in the lab frame. Right? And these, as I said initially, these are just the usual area elements. So this will give you d theta, d phi, sine theta in the lab, and then you divide this by d theta, d phi. But now let's just say this is center of mass. The d phi, you're just going to assume that this will be cylindrically symmetric. So you only need to find what is sine theta 1 d theta 1 over sine theta 2 d theta 2, and these are just what we have computed. So d cos theta 1 over d cos theta, and you can find what this derivative is directly from there. So if you then compute what is d cos theta 1 over d cos theta, this will give you, it's only going to be acting there, so this gives you 1 plus m1 over m2 squared cos theta 3 over 2, and then it hits there. I think I did it neatly somewhere. Okay. There. It's just that you're going to say that d cos theta, inverse will be the giving this. So that's why the thing that was in the denominator now has become in the numerator. And this will allow you to relate the quantity, which is easy to compute, which is the sigma over the omega measured in the center of mass. And this quantity is very easy to compute. I think in this lecture that will be our goal, to try and compute the sigma over the omega in the center of mass frame. So right. So if you look at the picture that I drew, the interaction actually occurs only for a small range. So for r greater than a, the potential, it only has a certain finite range. Outside of that range, that potential then will be zero. So it will mean that if you look at the particles that have been scattered before there, and by the time that you look at them in the detector, this radius r will be far greater. So it's outside of that range. So for most part, this, if you write the Schrodinger equation plus k0, for most part, this will be the free Schrodinger equation, and you can solve for what this psi would be. Let me just phi incident, which is the one here. Right? So phi incidence will just be, it's just the usual solution to the free Schrodinger equation. So these are just plain waves, a, e, I, k naught, r, k naught dot r, and these are three-dimensional vectors. Now, if you are assuming that you are dealing with an isotropic scattering, the scattered wave will be spherically symmetric, so it will be going like 1 over r e I k r. This is if you are assuming that your problem has pure spherical symmetry, but in general, this equation will not hold, but you will still get a fudge factor, so the scattered wave will still be going like 1 over r e I k r, but there's going to be this amplitude of theta of phi. And how then do you get that f? You find that f by solving the Schrodinger equation. So let me just summarize. So in summary, your wave function, you are going to say that it will be of the form, it will be just a superposition of the incident wave plus the scattered wave. So the incident one, it's just the free solution to the free Schrodinger equation. So this is just planar waves, ik dot r, plus this will be 1 over r e I k dot r, but there will be this scattering amplitude of theta phi. Right. And there will be this a, but in the end we will set a to be 1. So if you remember the definition for the scattering cross differential cross section, it will involve J incidence, and J incident, I think when we were in third year, we showed that for the Schrodinger equation, the flux is given by, in terms of phi incident, grad phi incident minus complex conjugate minus phi incident, grad phi. Right? And you know the form of the incident wave function, so to mu. So then this gives you a squared h bar k0 divided by mu. And similarly, J scattered will involve that function f there. So you get a squared h bar k over mu r squared f theta phi. So if you look at, if you try to rewrite, so the n will be given by j scattered r squared d omega. Then if you find what is, from this equation, you can read off what is dn by d omega. It's just j scattered multiplied by r squared. And you had already calculated what that j scattered was. It's going to be a squared h bar k over mu f theta phi squared, and by definition d sigma over d omega is given by 1 over j incident, and you had already computed what the j incident will be, so you get a squared h bar k 0 over mu dn over d omega, and dn over omega is that thing, so you get a squared h bar k over mu f theta phi squared. Most of the things will cancel, so you only end up with k divided by k0 f. This is just f squared, and because you are dealing with elastic collision, so k will be the same as k0, so this factor then will give you 1, and we have obtained the key result. So the differential cross section d sigma over d omega will just be given by the this this expression f squared. So it means that once we have determined or solved the Schrodinger equation and we have determined that function f, then we can quickly, directly, we already know what then the scattering cross section will be. Now we have been looking at the Schrodinger equation either very far away, but when you're dealing with the target, the equation that you have to solve will be just rewriting the Schrodinger equation, psi of r. This will give you 2 mu over h bar squared g of r, psi of r. Now the solution to this equation will consist of two parts. So there's going to be the equation that solves the free equation 0. So this will just be the homogeneous solution, but you still have to find what a particular solution. So to do that, you have to use the method of Green's function. Is everyone familiar with the method, or should I revise it quickly? Okay, since no one is answering, so right. So let's say that you have a linear, it could be a linear differential operator or any operator, and you have an equation L acting on mu gives you some function f, and so if the operator L has an inverse, meaning LG given by 1, I'll write it down as to what I mean, then it's clear as to how to solve that equation, because all you have to do is just, if you just add with L minus 1, L x acting on U, this will give you 1. So on the other side, you're left with just L minus 1 acting on F, and L minus 1 is defined to be this function G acting on F. So this means that you know the solution if you can find this operator such that when you multiply it, it sort of gives you 1. So G acting on F. So to manipulate this, I will hit this equation 1 by x, so you get, this gives you x acting on G acting on F, and then I insert a 1 there. So this gives you, and this is just u of x in the coordinate representation. So x, G, and my 1 will just be dy, y, y. Right. So this is just 1, but now it adds on that f. So you can take out everything out of the integral. So you get that your u of x will be given by dy, right? X, y, y, f. This is just dy f of y, x of y. Maybe not really. There's a g here, right? So this I'm calling f of y. So let me write it neatly. So the solution u of x is given by, if I write, let me write it again, g, then I inserted the 1 dy, y, acting on f. Then I took out the integral, so I get dy, x, g, y, and f. And this is called the equation g x of y, f of y. So this is the formal solution to the equation L acting on u gives you f. Right. Now this g acting on L has to give you 1. So you can repeat the same trick, sandwich x and y, x and y. And this equation, once you write it down, just tells you that Lx acting on the Green's function has to give you a Dirac delta function, delta x minus y. So the formal solution is given by some function, and this function has to satisfy uh, this equation. So if we go back to the particular equation that we wanted to solve, so it will mean that our wave function will be given by psi r. There will be this is just what I call the homogeneous solution, plus another thing that would be written in terms of a Green's function 2 mu over h bar g r minus r prime v of r psi of r. So this is similar to you trying to solve Lx acting on u gives you f. Our equation in this sense was d2 plus k squared. It's given by 2 mu over h bar v psi, right? So then this was given by g x y f of y. So you just multiply this thing by the Green's function, and then you integrate. So psi of r given, let me, psi incident plus 2 mu over h bar d3 r prime g r minus r prime v of r prime psi of r prime. This is the formal solution to the Schrodinger equation. However, we still have to determine what that function is, and to do that, you say that Lx acting on g has to give you a direct delta function delta x minus y. So that equation gives us, so we still have to solve the equation delta squared plus k squared g r minus r prime delta r minus r prime. So this is the equation that we will still need to solve. So we just decompose everything in terms of Fourier coefficients. So we write g of r minus r prime gives you 1 over 2 pi 3 d3q g of q e I q r minus r prime. Similarly, now for the Dirac delta function, I've given you this formula before. I think it was in homework assignment 1. Just that here now it's a three-dimensional version of the formula that I gave you. d3q e I q r minus r prime. Then you take this one, and then you plug it there. So once the Laplacian acts, it will act there. So you end up with, and it's bringing out a minus an IQ down. So this gives you minus q squared plus k squared. This g of q d3q over 2 pi cubed. I'm just saying that I'm just taking this expression and plugging it into that equation. So once the Laplacian hits on the exponential, you get the minus q squared, but everything is inside the three-dimensional integral. So that was the left-hand side. For the right-hand side, you just write 1 over 2 pi cubed d3q e I q r minus r prime, and then you just compare, right? So there's a d3q there, d3q 2 pi cubed, 2 pi cubed. So this will mean that and I'm missing that thing there. So this an e I q r minus r prime, right? So that term is the same as that term there. So this will mean that this thing here has to be 1. So, and you're done, because remember that you are looking for this function such that 1 del squared plus k squared, when it adds on that function, it gives you a Dirac delta function. And that function, you will know once you know what is g of q, and you've just solved for what is g of q. This has to give you 1. So this means that that g of q is going to be given by 1 over minus q squared plus k squared. Take this g of q and then plug it into the expression for the Fourier expansion for the Green's function. So whatever you found there, you just plug it there. So so we are done because we have formally solved for that function g. So let me write everything out. So we have found that g of r minus r prime given 1 over 2 pi cubed 0 infinity q squared dq over k squared minus q squared. This is what I was calling g of q, the thing in the denominator. But you still have to integrate out over the angular degrees of freedom, so we still have to integrate e I q r minus r prime cos theta sine theta d theta d phi. Nothing will be depending on the d phi, so that one will just give you 2 pi. Here you can change variables and let's see, call it x, but the integral over d theta is easy to do, 0 to pi. So you just get 1 over r minus r prime. It's basically the integral of e x a, right? And then this is sine theta d theta is just dx. So this integral will give you 1 over a. So this will just give you 1 over I q e I q r minus r prime minus e minus iq r minus r prime. Once you plug in the limits 0 and pi, right? And then there's that other q squared there. So one of them will cancel the one in the denominator. So you'll end up with that g r minus r prime is going to be given by 1 over 4 pi squared I 1 over r minus r prime. But you still have to do the integral 0 to infinity q e I q r minus r prime over q squared minus k squared. And the way that you do this type of integrals, you do by the method of residues. Okay. Right. So you have to choose a counter. So this has a pole at k equals to plus or minus q. So if you're in the complex plane, you'll have a pole there. You'll have another pole there. So the correct prescription that you have to choose is either choose that counter there. And that way, the only contribution coming will be coming from q equals to plus k. Or you could have chosen the other way around, where the only contribution will be coming from uh, that one then. But the residues, this is just 1 over k minus q, k plus q. So then the residue is always going to be 1 over 2k. Where is it? Yeah. And remember that there was an IQ. So once you set k to be q, you get ik r minus r prime over r minus r prime. But there is also the other one where you could have chosen the residue at try to compute the residue at the pole q equals to minus k. That one will come with a negative there. So we are only interested in waves that are outgoing. So this is the solution that we will be focusing on. Remember what was the point? The point was that our wave function will be given by phi incident plus d3r of some Green's function g or r prime v of r prime and psi of r. And this thing, we found that g of q was going to be given by q squared minus k squared. Then once we plugged it into g of r, this will be what we get. Now, this again should remind you of the Dyson series in the sense that you have an integral equation. Psi of r is unknown, right? So we don't know that, but it's also appearing inside the integral. And usually r for most regions is approximately equals to 0. Or I'm saying that for most regions, this potential is very weak. So it means that in the same way that we did for the Dyson series, we are going to ignore that part initially and say that, well, psi 0 of r is going to be given by phi incident. Then we take this psi 0, plug it into that equation. So that will give us psi 1 is given by phi incident minus mu over 2 pi h bar squared ei k r minus r prime over r minus r prime. But wherever there was psi of r, now we replace it by psi 0, which will be phi incident. And then we take this psi 1, plug it back again into that equation, and this will give you a psi 2. See, I think this is By this I meant this was psi 2. Now we have an expression, right? This expression. But I told you, or we had made a guess that our psi of r will be of the form phi incident, let's say, plus some function f theta of phi over r e I k r. We had argued before that the wave function will be of this form. Now we have the wave function, but it doesn't have this 1 over r, and it doesn't have the exponential. So what you do is that you look at, let's call this r prime, and this is the target, right? You have a detector which is very far away, so this will be r minus r prime. This is r hat. So for this type of scattering experiments, you always assume that r is way bigger than r prime. So then we look at what is kr minus r prime, using that assumption that r is way greater than r prime. So this will give you, let's just expand. So this is k multiplied by square root r squared minus 2r dot r prime plus r squared. But because r prime is very small, you can ignore those two terms, and you're just left with k and r. And similarly, you expand 1 over r minus r prime. This gives you, factor out the 1 over r, you're left with mod of 1 minus r dot r prime over r squared. This gives you 1 over r, 1 plus r prime dot r over r squared. Again, r is very small, so you can ignore that. So once you plug this into your previous equation, into 3, so 3 will be this equation. So you have just shown that 1 over the denominator will be behaving like 1 over r, and then that other part will be behaving like I k r plus some other factor, and you can then directly read off what this f of theta will be. It's just going to be the integral degree r of phi with there. You basically read off what this function will be. And remember that we had shown that the sigma over the omega is precisely given by this function f of theta phi squared. So it means that we have a theoretical expression to compute these differential cross sections. It's just going to be given by the square of the scattering amplitude. And we have found what that will be. Right. So in the Born approximation, you assume that your potential will be very weak. So V will be weak, so that your psi of r doesn't really change much from the incident plane waves that we're working with initially. So that means that you just put it's what I was saying, you say psi 0 if the potential is very weak, and initially you could have ignored that part. So this will mean that psi 0 will be approximately equals to phi incident, and then you take that phi incident and you plug it there where initially this was psi of r prime. So we're just saying that psi of r is going to be approximately given by phi incident, and phi incident, remember that it's a I k naught dot r. So you end up with that d sigma over d omega, which will be given by mu squared 4 pi squared h bar to 4 integral. Now you get e I q dot r g of r d3r. And because we're dealing with elastic collisions, the first thing that we could try to do is to compute what is q. So q will be given by k naught minus k, which is square root of k naught squared plus k squared minus 2k k0 cos theta. For elastic, k naught squared is the same as k naught. It's the same as k squared. So this gives you 2 square root 2 1 minus cos theta, and square root of 1 minus cos theta is sine squared. So this you end up with k squared. You end up erase. So q will end up giving you k square root 2 1 minus cos theta, which is k to k sine theta over 2. Right. Which is what you need there, which is that q there. Now I'll have to simplify the expression further, so let me just write out the integrals eiq dot r v of r prime d3r prime. This gives you v of r prime r squared dr prime, but you still have to integrate out over the angles. The angle over d phi, because nothing depends on phi, will just give you 2 pi. And then you will still have to do the integral from 0 to pi e I q r prime cos theta prime sine theta prime. So you can call cos theta to be x. So this gives you e I q r x. Then dx will be sine theta d theta. Then that integral just gives you 1 over I q r r. Right. Then e I q r x minus 1 to 1. This 1 over r will cancel one of them there, so you're left with r, u of r, q of r. And this is the final result of, I think, today's lecture. It's just that d sigma over d omega is given by that expression. So whatever potential I give you, you just multiply it by r, and then multiply it by sine qr prime, and then you do the integral. So in the example that I gave you, it's the usual one. So Rutherford scattering, or scattering through a Coulomb potential. So calculate the differential cross section in the firstborn approximation for a Coulomb potential. And to have a qualitative idea about the cross section derived in A, consider the scattering of an alpha particle from a gold nucleus. Right? If the scattering, like so, let's go. So d sigma over d omega will be given by f of theta phi squared. And this expression we just computed, it's 4 mu squared over h bar 4 q squared integral 0 to infinity r v prime r prime sine qr dr squared. So, and v of r for coulomb, so plug, so v of r is going to be z1 z2 e squared over r. So this gives you d sigma over d omega. I'll type this solution out. It's just that in the version that I gave you, it's not there. So you just square, right? Because this is coming with that square there, so you end up with z4 z1 squared z2 squared e to the 4 mu squared over h bar 4 q squared. And then you do the same trick that I asked you in the test last week. It's best for these types of integrals to use things like sine phi to the ei phi minus ei phi minus over 2. So you then have to do, there's going to be 1 over 2i integral from 0 to infinity r prime 1 over r prime eiq r minus e minus I q r. Right. Now the r's are going to cancel, and I have a feeling that these are going to start to diverge. So you have to introduce, to regulate your integrals so that they don't blow up. So I'm going to introduce another parameter lambda, and in the end I'll set it to 0. So you end up, basically we still have to do the integral from 0 to infinity of sine qr. So I'm saying that that integral, I will write it as limit. I'll introduce some parameter that I set to 0 in the end, 0 to infinity of e to the minus lambda r sine qr, and then you write this as an exponential. I'm sure you did this for the test, so you just repeat what lambda going to 0, and you will get lambda minus iq minus 1 over lambda plus iq. And then once you take lambda to 0, you just get 1 over q. So this means that the sigma over d omega is going to be, just write everything out, 2 z1 z2 mu e squared over h bar squared q squared squared q squared. And I think I did show in an earlier slide that q was proportional to sine squared, I think theta over 2. So once you square that, you get sine to the 4 theta over 2. And if I write it out, and this is a famous result, the sigma over the omega is given by 2 z1 z2 mu e squared over h bar squared q squared squared sine minus 4 theta over 2. This is the result that was obtained by Rutherford when he was scattering. This is how the atomic nucleus was discovered by Rutherford when he was scattering his alpha particles of void nuclei. Now there's that issue. So in the lab frame, theta is 60 degrees. So what you do is that you measure the theta in the lab frame, but these calculations are done for the lab, so you still have to move from the lab frame to the center of mass frame, which is where these calculations were done. So I derived this equation tan theta. It's just that I think in the beginning of the lecture, what the problem was that the thing that was sitting here was a ratio of velocities, and we used two ratios of masses that are easier to compute. That's why I think I spent to maybe 10 or 10 minutes just going through that derivation. The point of the first part of the was to show that VCM over V1L was given by M1 over M2. And for these ones, M1 and M2 are proportional to the atomic numbers, the ratio. So it's going to be 4. So this just gives you 4 over 197. So you get that 1060 is going to be given by sine theta over cos theta plus 0.023, which is just the ratio of the masses. And this theta 1 as measured in the lab, it's there, it's 60 degrees. And from this expression, you can try to solve for, you can try to use mathematical to solve for the angle. And you find that the theta, which is the one that you have to plug there, is given by, found this to be 61 degrees. Let me just check, yeah, it's 61 degrees. So you find that theta is given by 61 degrees. So the question B was consider the scattering to have a quality about the cross section derived in A. Consider the scattering, right? So they are looking for a numerical value for that. So we get, and we already, the point was that you cannot take the 60 degrees in the lab frame and plug it into the formula. The formula that we have been deriving using the Born approximation and so on. Those formulas are for the center of mass frame. That's why we had to first convert this into that theta in the center of mass frame to be 61 degrees. This is the angle that you need to work with as measured in the center of mass, not the one in the lab frame, but the measurement in the lab frame is easier. It's just that in terms of calculations, it's easier to work with the center of mass. And we already derived the formula that relates those two frames. So then you just do the sigma over the omega. Now you're just plugging in the number, so you get 2 times 29 divided by, let's see, we had Z1, Z2, right? Everything times, and there was a ratio of the energy, right? That ratio in terms of the fine structure constant, 4 squared. When you introduce that alpha, you're going to introduce bar C over E squared. So there will be these numbers, and then sine to the 4, sine to the minus 4 of theta over 2. Right? So you get 4 times fine structure constant is 1 over 37, square that. H bar C, you can check in terms of MeV, it's given by 197.3 MeV per Fermi over 8 MeV. They told you the energy of the incident flux. There it's 8 MeV, and then you still have to say psi minus 4, 30.5. It's not 30 because, as I keep saying, it has to be in the center of mass plane. Then once you plug everything there, you get you get 30.87 Fermi squared. And if you write out what those Fermis are, this gives you 0.31 times 10 to the minus 28 meters squared. And this is the unit for differential cross section, and it's called a bun. So this just gives you 0.31 bun, and one bun is just 10 to the minus 28 meters squared. So as I was saying, I'll type this, but in general you will be given some potential, and then you just plug it into this formula. I think that this is the key take-home message for this lecture. Are there any questions? So for those who came in late, I've mentioned this issue that the first question, most people were not able to get it. So I won't be, maybe I might give maybe 1 mark for the exact result, but I will only be interested in whether you were able to make use of perturbation theory correctly. And I gave, I can find it. So E1 was 0 for this first question. It I wrote it down. So I think we can end there. Are there any questions? Pleasure. If there are no further questions, I will close the session. Pleasure.